Hello friends, welcome back to the fourth part of the topic column bases, where in my first three lectures we just understood some introductory part on what is column basis, its definition, its use, functions. Then after we just saw what are the types of column bases, that is slab base, gazetted base and pocket base foundations. Then at first we understood in detail with what is slab base foundation, its introduction, its diagram, its design criteria for minimum thickness of the slab, and the IS code clauses what are important for this. Then after, on the second number, we saw what is gazetted base foundation. Again, its introductory part, its components. Then we saw the figures and different views for the gazetted base foundation, why is it used, its functions, all these things we understood. And in this lecture we are going to continue an example for design of slab base foundation. So quickly we'll start with the question and I'll just read out the example. Let me change the pointer. Design a slab base foundation for a column ISHB 350, that is Indian Standard High Beam 350. This 350 indicates the depth of the beam, and rest of the criteria for this entire section will be understood from steel table. So basically we have to design a slab base foundation. Section used for the column is ISHB 350 to carry a factored axial load 1200 kN. The load, this load is actually factored, that is it has been considered with the factor of safety. Assume Fe410 grade steel and M25 grade concrete. These are the two things given. Fe410, Fe indicates iron. This 410 indicates ultimate strength. And M25 grade concrete. These all things are given, and we have to take the safe bearing capacity of the soil as 200 kN per meter square. So this is our question, and what we need to do is to design a slab base foundation for the given information. Let us continue with the example, the solution. For steel Fe410, this is given in the question. Fe410, this Fe indicates iron, 410 is the Fu, that is ultimate strength. And we know that when Fu, that is ultimate strength for any given section, is 410, at that time from introductory part on IS code, yield strength is 250 Newton per mm square. So now we are having Fu410 and Fy 250 Newton per mm square. This is our Fu. And M25 grade concrete is given, that is FCK. This grade of the concrete is represented as FCK 25 Newton per mm square. So this is the data given. Now for ISHB 350 column, that is Indian Standard High Beam 350 column, we are having the specifications from the steel table. I'll just show it to you, but before that I'll just explain you this figure, the cross section of the compression member, or we would say cross section of the column here. That is this top is known as flange, this is known as web, this is the web. Now height is 350 given in grade of the section itself. This 350 indicates the height, or we can even say depth, but here we would indicate it by height. This is H 350. Rest of the criteria, that is BF, TF and TW, that is width of the flange, thickness of the flange, thickness of the web, all these things are given here, and the details are given in steel table. Let me just show you. That is this. See, this is our steel table, where these details are given on page 14. That is for rolled steel beams, and what we need to check is for ISHB 350. And see, here everything is mentioned in this row. The depth of the section here is 350 as shown here. Then width of the flange, that is 250. So here it is shown that width of the flange, this is 250 BF. Then we have thickness of the flange as 11.6. So here it is given TF 11.6, this thickness of the flange. Now what we are concerned is with TW, that is thickness of the web. So we verify that thickness of the web is, here it is mentioned, it is for IS HB 350 it is 8.3 here. So that is what I mentioned over here. So in this way I have noted all the things from the steel table, and now I am having the value of this BF, this TF, this TW, this H, everything I am having. In short, I am having the dimensions of the cross section of the compression member, what I am informed to design the slab base foundation for. Now moving further, our next step is to find out the area of the base plate. The base plate is actually located below this column in order to support the column. So first of all, what we need to find is area of this base plate. For finding out the area of the base plate, we are having the formula, this factored load divided by bearing strength of the concrete. So for that, what we need is two things, factored load and bearing strength of concrete. Factored load is given directly right in the question, that is 1200. See, here it is given 1200 kilonewton. So we'll just convert it into Newton and mention here 1200 into 10 raised to 3 Newton. But what is bearing strength? Actually bearing strength is 0.6 into FCK. This is mentioned on IS code 800 2007 clause 7.4.1 on page 46. That in order to find out the bearing strength of the concrete, we need to multiply the grade of the concrete with 0.6. That is 15 Newton per mm square. So now we are having both the values PU and bearing strength of the concrete. That is the 1200 into 10 raised to 3 divided by 15. So in this way we are having area of the base plate as 80,000 mm square. See, we are not having thickness. What we are having is just a area of the base plate below this, like it is located like this. We are not still aware about the projections of the base plate or the thickness of this base plate. What we are aware is only about the top, this much area of the base plate, that is 80,000 mm square. Now size of plan in column. Now as discussed earlier in the theoretical portion, we had a talk regarding the projections. If we are providing a base plate like this, then one of the projection is A and on other side it is B. One is the shorter and one is the longer projection, but according to our discussion, we are taking both the projections as 50, that is 50 mm. So size in plan is B is 350, this is 350, and BF is 250, this is 250. Let me remove unnecessary things to avoid the confusion. Okay, yes, this is a B, this is A. We are talking about projections. Provide 50 mm equal projection on all the around the column, right, as we did here. Both of these A and B are 50. So now we can decide the area of the base plate, or we can say that we can just check for the area of the base plate. If we provide this, then we are having this much 250, and on both the side if we are taking 50-50, then 250 plus 100, that would be 350. See this, shown it over here, D, and we are denoting it as DP, that is width of the base plate. And again, regarding another dimension, that is this dimension of the base plate, this B is also 50. So overall here is 350 plus 100, that would be 50 plus 50, that is 450 mm. So in this way we have fixed the dimensions of the base plate. That is, remove everything, show it again. dimensions of the base plate are mentioned here. That is, one is 450. This dimension becomes 450, and this one becomes, sorry, I made a mistake. Actually this is 450 because the longer web side it is, and this is actually 350. As we found over here. So we are using the base plate of 450 cross 350, and we can say that the gross area of the base plate is 450 cross 350, that is 157500 mm square. That is gross area of the base plate. This is our first step to identify the area of the base plate. Then after moving further, our next task is to fix the thickness of the base plate. As we just saw the formula in the design criteria for the base plate in Slab Base Foundation, and it is given on page number 47, IS 800 clause 7.4.3.1, where both the projections A and B are taken as 50 mm. Here is the figure, but we'll understand this later. We'll continue with the example. For the deciding the thickness of the base plate, what we had, the formula is this one: Ts is equal to 2.5 into W into A square minus 0.3 into B square into gamma m0 upon Fy, and it should be greater than this Tf, that is thickness of the flange. So at first we'll see what is this W. W is actually the uniform pressure on the base plate, as we saw in the design criteria. And how can we find the pressure is load divided by area. That is the pressure, that is overall factored load divided by area of the base plate, that is gross area of the base plate, 450 cross 350, what we just found, and this is given in question itself, but we just converted into Newton. So our answer is W is equal to 7.62 Newton per mm square, that is uniform pressure on the base plate. So we found out this. We are having A and B as 50, gamma m0 we are having 1.10 according to table number 5 in IS code 800 2007. Because it is a plate, we are taking 1.10 here. And regarding Fy, that we already had discussed earlier, that is for Fe 410 grade steel, yield strength is 250. So solving this equation, we are having the answer 12.11 mm thickness of the plate, but this size or this thickness of the plate is not available, so what we are taking is 14 mm. Now checking for the condition, it should be greater than thickness of the flange. So we can say that 14 mm should be greater than thickness of the flange. Now what is thickness of the flange here? We will just check. It is 11.6. So 14 is greater than 11.6. So our design is okay, for our design of the base plate is okay. Hence base plate is of dimensions 450 cross 350 and 14 mm thickness. And we are providing 420 mm diameter bolts and 300 mm long anchor bolts, we can say, to connect this base plate and the foundation concrete block. As we discussed earlier from the figure, let me show you. This figure. Anchor bolts 20 mm diameter and 300 mm in length. This length. Moving further, now we'll talk about the weld connecting the column to the base plate. Now along with the bolted connection, we are even providing the welded connection, that is we are providing a fillet welding around this connection of this I section or column with base plate. These two things we are connecting even with bolt by using angles, or we are using a plate here, I mean a fillet weld here. See, this is the fillet weld on this side. So again, as we discussed all the criteria for welded connection or fillet weld properties, we will use the same criteria over here, and all the IS code criteria for welded connections are given in IS code 800/2007, page number 79. So let us just continue. We are using a 6 mm fillet weld, or we would say we are assuming that we are fixing that 6 mm fillet weld all around the column section to hold the base plate in the position, right? Now we'll check whether this 6 mm is okay or not. The total length available for welding along the periphery of ISHB 350 is, so we are fixing the total length. I mean, at what is the effective length of the welded connection required. So that is dependent on the dimensions of the I section, right? So let us check. This is 350. Again, this is 350. So we can say 350 into 2. But for this, again, this is 250. This is 250, but this much is subtracted. So 250 plus 250 minus this is 8.3. So this is what I have explained over here, 250 minus 8.3. And this much BF is written over here. And everything is multiplied by 2 because it is on the both the side. Again explaining you, this is 250. This is 250 minus 8.3. This thickness is neglected. The same thing is over here. So we can say that 250 plus 250 minus 8.3 into 2, and this 350 on this side, again this 350 on this side. I mean both this side. So again we are multiplying 350 also with 2. So total linear length, if we consider running length of the fillet weld, if we consider, it is 1683.4 mm. But see, we have not considered the end returns here. End return in the sense we are not welding, or we are not considering the end returns, or we are leaving some of the space at the ends, as we had discussed in welded connection, right? That is 2 into size of the weld. That much we are neglecting or minusing at each and every end. Now at first we need to identify how many ends are actually there in this I section. So let us just check. For any I section, I will draw another I section. For any I section there are actually 12 ends. Number of ends we'll talk about. So this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So there are 12 end returns in any I section, we would say. So depending on the number of ends, 2 into S will be subtracted from the total length. That is 2 into size of the weld, that is minimum leg size, that is 6, as we had fixed it over here. 2 into 6, that is 12. 2 into 6 is 12. 12 into number of ends, that is 12. So our answer is 144 will be subtracted from this 144. So our answer is 1539.4 mm effective length we have calculated, and that was total length. Now in order to identify the capacity of weld per mm length, we have formula 0.7 into S into FWD, where 0.7 into S is size of the weld 6 and FWD is 189 because it is shop welding. As we had discussed in welded connection, everything is given in clause 10.5.7.1 IS 800/2007, considering P LW into throat thickness into FWD, where LW is 1 mm because we are only calculating for per mm. So FWD is 189. This everything is given here on clause 10.5.7.1. I am not going in detail over here because it is covered under welded connection, and the factor of safety taken here was 1.25 because it is shop welding, but we can directly remember that it is 189 for shop welding FWD, because we are not welding this on field, so it is shop welding and it will be always 189. So our answer is for capacity of weld per mm is 0.7938 kilonewton per mm, or we would say 793.8 Newton per mm. Now if we are calculating for kilonewton, then again the factor load will be in kilonewton. If we are calculating in Newton, then factor load will also be in Newton. We can use either of the thing, but we are using kilonewton per mm right now. So required length of the weld. Now what is the length of the weld actually required? So required length of the weld is 1200 factor load divided by 0.738 capacity of the weld. So our answer is 1512, that is less than 1539 what we calculated here. So this was just a check, and so 1539.4 is okay, and 6 mm weld is adequate to use for this fillet weld. Moving further, now we'll talk about the size of the concrete block. Now what size of concrete block is actually required below the base plate? At first we are having the column, below that we are having a base plate, and again below that we are having a concrete block. But we need to fix the dimensions of this. At first we just talked about this dimension, column dimension, then we talk about base plate dimension, and now we are talking about this concrete blocks dimension. Axial load on column is 1200 kilonewton. This is factor load, but we need to calculate working load. What is the working load? That is, we'll divide it by 1.5. The answer is 800 kilonewton. Now the factor load we have converted to working load. But see, we have not considered the self weight over here. So we need to add something with this 800 kilonewton as a self weight. That is 10% as the self weight of the concrete block. So the 10% of this is 80. So total will be 880 kilonewton as the total load on the column, or we would say that total load acting on the foundation. That is 880 kilonewton. Now area of concrete block required. Now we'll talk about the area of concrete block required. In order to find the area of concrete block required, total load divided by soil bearing capacity of the soil. So here our total load is 880 kilonewton and soil bearing capacity is 200 kilonewton per meter square. So here our answer is 4.4 meter square, and we know that concrete block is designed for working load, right? That is why we have calculated this 880. So our area of concrete block required is 4.4 meter square. But we just have got the upper area, we haven't decided the thickness. I mean, we don't have this thickness of the concrete block. We just have is this area. That is 4.4 meter square, and we are not even knowing with the length and width of the block. So we'll decide length and width first. Now to find out length and width of the concrete block, consider a rectangular concrete block with equal projections beyond the base of the plate. Suppose this is our base plate. Equal projections we are talking about, that is, suppose we are taking X on both the sides. This is the boundary, I mean this is the line of our concrete block. This. Now say X we are taking as the projection. So one of the dimension of our base plate, if we talk about in meter, is 0.35, this, and one of is 0.45 meter. Now in order to calculate the length and width, what we are having is area. Total area only we are having, that is entire area of this concrete block, top surface. I'll just remove these lines. So area is equal to length into width. Now length is 0.45 plus x, that is 2x. 0.45 into 2x, that is what I have written here, into width, that is 0.35 into x again 0.35 into 2x. So solving this equation, we will have the value, or we would say we have equation at first, 4x square plus 16x minus 4.2425 is equal to 0. This is our equation, and solving that we will be having value of x 0.849 meter, and we'll take x as 0.85 meter, one and the same. So we'll just add this value of x to the value of this base plate. 2 into x will add. So these are the dimensions. Length is 0.45 into 2 into x, width is 0.35 into 2 into x. So length and width of the column block are shown here, 2.15 and 2.05 meter. Now area of concrete block provided is, multiplying both length and width, that is 4.407 meter square, and that is greater than 4.4 meter what we just found previously. Yes, it is greater than this, therefore it is okay. Now we need to fix the depth of the concrete block. In order to find the depth of the concrete block, we'll talk about the depression angle. See, we are having the value of this x 0.85 what we just found. We are taking this angle as 45 degree. We have to take this angle as 45 degree. This is 0.85. So if we are having one side, one angle, then we can even have the other side. Tan theta is equal to adjacent side upon opposite side. I mean tan theta is equal to opposite side upon adjacent side. In this way we can calculate the value of this opposite side, that will be even 0.85 because tan 45 is 1. So depth of the slab is also 0.85. So in short, we have decided the the dimensions of the concrete block as 2.15 cross 2.05 cross 0.85 meter. Here it is mentioned. So in this way we found each and every details for using the slab base foundation. This is all for today. Thank you for watching and wait for the next videos.